So what we're going to discuss is something called oxidation and reduction. So this is a specific type of reaction that we call a redox, combining the terms reduction and oxidation. So oxidation is a term you've probably thought of or heard of from biology or from some other maybe science course. Oxidation is something that occurs here, and it's not always involving oxygen. So it's kind of interesting thinking of it that way. So what it is it's a redox reaction describes all chemical reactions where there's a net change in atomic charge. So there's a couple different ways where a redox reaction can occur. When you form a compound from its elements, you have a redox reaction. Combustion reactions are all redox reactions. Reactions that create electricity, and reactions that produce cellular energy. So batteries are examples of redox reactions. There's a redox reaction going on inside of it, which provides the voltage for the battery for whatever purpose you're trying to run. So we have oxidation. Oxidation is the loss of electrons. So you can think of oxidation as gaining more positive charge. Reduction is gaining, and the formatting is a little bit odd here, but it's the gaining of electrons so the atom can gain a more negative charge. So there's a couple ways to help you remember this. Leo the lion goes grr. So Leo stands for loss of electrons is oxidation, and grr is gaining electrons is reduction. There's also oil rig, which stands for oxidation is losing, reduction is gaining. Either way, they're little things to help you. There's also one called a Redox, which kind of is the same idea. So here's an example here. Here we have the copper plus 2 ion becoming copper solid. So copper plus 2, we've worked with this. This would be a blue solution. And this is going from a blue solution, so the copper dissolved, to a solid, so like a penny, the reddish orange metal in this case. So in this reaction, we're gaining electrons. So in this reaction, the copper is being reduced. In the next example, we have iron, solid iron, such as the iron in steel, becoming the iron plus 3. So in this one's the opposite, so it's going to be oxidation. So rusting is an example of this. When you have rust that's occurring, you're going from iron that's solid in steel to that brownish, crumbly iron oxide is an example of that. So oxidation reduction is kind of a key idea here. So an oxidizing agent is what does the oxidizing, but it gets reduced. The reducing agent does the reducing, but it also gets oxidized. So this is one of those things that makes you kind of think for a moment. It's kind of confusing. So I like to first identify what's being oxidized, what's being reduced, before I identify the agents. Okay, so in order to figure this out, I take a look at what's being oxidized and what's being reduced. So in this example, aluminum is going from aluminum solid to aluminum plus 3, which is oxidation. Therefore, the aluminum that's the solid is the reducing agent. And then the opposite for the copper plus 2. That's your oxidizing agent going from copper plus 2 to copper solid. I'm not going to really ask you about this because this is super confusing. So you can kind of put an X through number 6. If you go on to take a more advanced chemistry course, they will talk about this in more depth, and it will be something you were responsible for. So oxidation numbers. This is what an oxidation number is the same thing as a charge. So what we're looking at is what are the charge of the substances that we have. So there's a few rules we have to help us determine this. This is key for us to determine the redox reaction is occurring. So for ionic compounds, it's going to be its charge. For covalent compounds, it's not always obvious, so there's some rules that we have. So the first one is for an atom in its elemental form, such as sodium or oxygen, the oxidation number is 0. So anything that's elemental has an oxidation number of 0. For something that's an ion, it's going to be its oxidation state. So if we have the chloride ion, it's going to have a -1 charge. So all of that naming with the ionic compounds is going to come back with us. So for covalent compounds, that's where it gets tricky. All molecules have an overall charge of 0 unless they're an ion. How do we know they're an ion? They have a little negative something or positive something in the corner, the little superscript. So for everything else, we're going to follow the following rules. So group 1A on the periodic table are going to be +1. This is exactly the same as what we've been doing. Same for group 2, +2. So for hydrogen, is +1 in combinations with nonmetals. So like in hydrochloric acid, hydrogen is going to be +1. Most often, hydrogen is a +1. Sometimes when it's with metals and boron, it's going to be -1. But usually it's +1. Fluorine is going to be -1 in all compounds. Oxygen is -2 in most compounds, except if it's with an F or a peroxide. So these exceptions, we're not really going to be looking at the exceptions. We're looking at more of the big picture here. And then group 7 is -1 in combination with metals or nonmetals, except some of the ones in the lower group. Okay. So the first thing we have to do is we have to practice identifying our oxidation numbers. So the first one we have is nitrogen gas. Nitrogen is a member of the diatomic group. So nitrogen is diatomic. So this is nitrogen in its elemental form. Therefore, the oxidation number, which we abbreviate ON, is going to be 0 here. Nitrogen is in its elemental state. When I'm doing these, I like to identify the ones that are in their elemental state to start with, because those are the easy ones, because they're 0. So the other example of something in its elemental state here is lithium. Lithium, oxidation number is 0. Then letter B is a normal ionic compound that we're used to seeing. We know the oxygen is -2 and the calcium is +2. So that follows all of our traditional rules. That one we're used to working with. What makes this a little bit trickier is when we get to something with a polyatomic. So for example, we have KNO3. KNO3 is tricky because we have that nitrogen. Potassium we know is +1 because of the rules that we have, and oxygen is -2. Now, we do have 3 oxygen, just like before. We're going to multiply the charge by the quantity, so we're going to have a -6. So we have a +1 from the potassium and a -6 from the oxygen. When we add all of these up, it has to equal 0. There's no charge here. This is not an ion. So we have to figure out what's the charge of nitrogen. So based off of the information we have, we're going to say the nitrogen is +5. I generally write the oxidation numbers with each element. Sometimes if it's really small, you have to kind of squeeze it in, or you can write it out like K is equal to +1, N is equal to +5, and O is -2. So the next example, we have 4 different elements, which makes it a little bit tricky. So the sodium is +1 because it's in group 1. Oxygen is -2. We have a hydrogen and a sulfur. So hydrogen is usually +1, and it is in this case because it's bonded with nonmetals. So the only thing we have left is the sulfur. We do have to take into account any quantities we have. So there are 4 oxygens giving us a total -8 there. We have a +1 from both the sodium and the hydrogen. So we're going to end up with sulfur being a +6. Why 6? Well, we have a positive 2 from the sodium and the hydrogen added together, and then negative 8 from the oxygen. That gives us sulfur as positive 6. So calcium carbonate, we have plus 2 from the calcium, minus 2 from the oxygen, which will give us plus 4 for the carbon. Next, we're going to do water. Oxygen is minus 2. We have 2 hydrogens, each is plus 1. So it actually ends up working out because we'll have a plus 2 from the total hydrogens and a minus 2 from the total oxygens, adding up to 0. The next one, we have a negative charge. Sometimes you'll just see the negative sign. I like to include negative 1 to make it clear that it is 1, but sometimes you will just see the negative. So we're going to follow the same rules that we've been following the whole time, except now instead of adding up to 0, it's going to add up to negative 1. So oxygen is a minus 2. So overall, we have a negative 4 charge. So negative 4 plus whatever nitrogen's charges has to equal negative 1. So that means nitrogen has to be plus 3 here. So nitrogen is plus 3. Plus 3 minus 4 is negative 1. It has to add up. So you'll notice in an earlier one where we had nitrogen, it was 0. Nitrogen is one of the elements that can change a lot. And then on the other side, I think we had nitrogen being 5. So nitrogen is going to be one that we work with a lot. Last but not least, we have this. This is a polyatomic called dichromate. This wasn't one you needed to know, but we follow the same pattern. So we have a negative 2 for each oxygen, giving us negative 14. So negative 14 has to equal negative 2. So we have 2 chromium, so it has to be 2x. That's kind of how I think of it. So it's going to be x is equal to positive 6. So chromium has to be positive 12. Each chromium is going to be positive 6. So we're going to do the same thing that we did above, but we're going to do it for each compound. So in this example, we have hydrogen and oxygen, which are both in their elemental state. So they both are going to have an oxidation number of 0. Water we had above. We know oxygen is negative 2 and hydrogen's positive 1. So what we generally do is we connect them. So we're going to take the hydrogen and connect it to the hydrogen, the oxygen, connect it to the oxygen. So we're going from a charge of 0 to a charge of positive 1 for the hydrogen. In order to do that, we have to lose electrons, which makes this oxidation. Remember, LEO, losing electrons is oxidation. Oxygen is going from 0 to negative 2. So oxygen is gaining electrons, or GR, which is being reduced. You might be thinking, well, why isn't oxygen being oxidized? Oxygen doesn't have to be oxidized. It can be, and usually is, but isn't 100% of the time. In this case, oxygen is being reduced. So if you look at the next example, it is a little bit more complex, but copper's in its ground state. We've done some of these substances already. Water, we know oxygen is negative 2, and then the hydrogen is positive 1. We'll have to go through and identify the remaining ones, though. So hydrogen's positive 1 in nitric acid. Oxygen is minus 2. So we have plus 1, minus 6, meaning nitrogen has to be plus 5. Notice we would call this a polyatomic ion of nitrate. We have the same thing here. So you could just kind of say plus 5, minus 2 for your nitrate because it's the same thing. And copper is going to be plus 2. So if you know how to identify it because of the polyatomic ions, we know nitrate's the same. You don't have to calculate every single one. Once you do it once in your example, you can use the same numbers. However, NO2 is not the same. That's not nitrate or nitrite even. That's nitrogen dioxide. So oxygen is -2. We have 2 of them giving us a -4 charge. So that means nitrogen has to be +4. So what we're going to do in this example is we're going to take a look. We're looking for changes. So I'm going to go through and highlight things that change. So for example, copper is 0 and +2. So that changed on both sides. Hydrogen didn't change. Oxygen hasn't changed, but nitrogen has. We're only going to use the nitrogen that changed, though. We're not going to use the one here. So not all of the nitrogen is changing, just some of it. So then we're going to connect those together. Zero to +2 means we're losing electrons. Losing electrons is oxidation, meaning nitrogen is gaining electrons, which is reduction. So again, this was a little harder example. Why don't you try letter C on your own? See if you can identify what's changing. So you should have ended up with copper being oxidized and oxygen being reduced. So in order for one to be oxidized, you have to have reduction. You can't have one without the other. Because what this is doing is we're transferring the electrons. In the last example, it's the same kind of thing. So why don't you try this one? So you should have ended up with sulfur being oxidized. It goes from -2 to +4. And oxygen being reduced. It goes from 0 to -2.